Have you ever wondered how your email reaches its destination error-free? Or how your video streams smoothly over the internet? Dive into the world of transport layer protocols within the TCP IP suite, a critical component ensuring that countless bits of data find their way across the digital cosmos. At the heart of this layer are two primary protocols, each playing a pivotal role in how information travels through the network: TCP, or Transmission Control Protocol, and UDP, or User Datagram Protocol. TCP is the stalwart of reliability, ensuring a connection-oriented path where data packets arrive in order and without error. This is vital for applications where the accuracy and completeness of the information are paramount, such as in web browsing, email exchanges, and file transfers. On the flip side, UDP offers a connectionless service, trading reliability for speed and efficiency, making it ideal for real-time applications like video streaming and online gaming where every millisecond counts. Understanding these protocols can illuminate how our digital world ticks. Transmission Control Protocol, or TCP, is often the unsung hero behind your uninterrupted online experiences. Let's delve into the workings of this cornerstone of internet communication, which ensures that your emails, web pages, and files arrive not just promptly, but correctly. TCP is known as a connection-oriented protocol. This means that before any actual data transmission occurs, TCP establishes a connection between the sender and receiver. This setup is crucial because it sets the stage for a reliable communication channel. The process starts with something known as the three-way handshake. This is TCP's way of initiating a conversation between two devices. Firstly, the sender sends a message called a SYN, synchronized packet, to the receiver, indicating the desire to establish a connection. The receiver then responds with a SYN-ACK, synchronize-acknowledge packet as a confirmation. Finally, the sender replies with an ACK, acknowledge packet. Only then is the connection considered established and the actual data transfer can begin. Now, why is TCP so reliable? The answer lies in its robust mechanisms like error detection, acknowledgement, and retransmission. Imagine sending a crucial email. TCP ensures that every single bit of your message is received exactly as sent. If any part of the data goes astray or arrives corrupted, TCP detects these errors and triggers a retransmission of the affected data packets. Additionally, every packet that arrives safely at its destination is acknowledged by the receiver. If the sender does not receive this acknowledgement, it will resend the packet. This meticulous process guarantees the integrity and completeness of the data transferred, but TCP doesn't stop there. It also incorporates sophisticated features such as flow control and congestion control, which are essential in maintaining the quality of the network. Flow control prevents the overwhelming of the receiver by regulating the amount of data sent. On the other hand, congestion control helps avoid network traffic jams by adjusting the rate of data transmission based on the current state of the network. These features work together to prevent data loss and ensure efficient use of the network, even when it's under heavy load. By managing each of these aspects meticulously, TCP provides a stable and dependable platform for communication over the internet. It's like having a highly skilled conductor, ensuring that every section of the orchestra plays in harmony, perfectly synchronized, without overpowering each other or missing a beat. So TCP not only connects devices, but also ensures that every piece of data reaches its destination perfectly intact. But what about situations where speed is more crucial than perfect accuracy? In the digital realm, not all scenarios demand an immaculate transmission of data. Enter the User Datagram Protocol, or UDP, a connectionless protocol that prioritizes speed and efficiency. Unlike its counterpart TCP, which establishes a connection and ensures that all packets arrive in order and without error, UDP takes a more laissez-faire approach. It sends data without prior communications to set up special transmission channels or paths. This means UDP can transmit messages with much lower latency compared to TCP. So, where does UDP truly shine? Consider real-time applications such as live video streaming or online gaming. These are environments where a delay of even a fraction of a second can detract from the user experience. In such cases, it's preferable to miss a packet or two rather than experience a lag. UDP's ability to send data quickly makes it ideal for these time-sensitive situations. However, this speed comes with its trade-offs. UDP does not guarantee that all data will be delivered, nor does it ensure the order of data packets. This means that error correction and ensuring delivery must be managed by the application itself if needed. Many applications compensate for UDP's lack of reliability with their own error checking and recovery mechanisms, thus maintaining a balance between speed and data integrity. In essence, UDP's design allows it to deliver data swiftly, sacrificing reliability for speed and efficiency. Now that we understand both TCP and UDP, let's compare them side by side. Transmission Control Protocol, or TCP, is like a meticulous planner. It establishes a connection before any data is sent, ensuring a reliable pathway is in place. This connection-oriented nature makes TCP akin to a courier service that confirms delivery of your package. On the other hand, User Datagram Protocol, or UDP, is the spontaneous traveler of the network world. It sends packets without prior connections, making it faster but less reliable than its counterpart. In terms of reliability, TCP is the champion. It uses acknowledgments and retransmission mechanisms, ensuring that no data is lost or corrupted along the way. It's like double-checking that every letter of your message is delivered correctly. UDP, however, takes a more cavalier approach. It doesn't wait for acknowledgments, leading to potential data loss. This is acceptable in scenarios where speed is more critical than precision, such as live video streaming or gaming, where a slight imperfection or data loss won't spoil the experience, but a delay would. Applications choose between TCP and UDP based on these characteristics. For instance, applications requiring high reliability and data integrity, such as web browsers, email clients, and file transfer services, overwhelmingly choose TCP. They benefit from its methodical and error-checking approach, ensuring that all data reaches its destination correctly and in the right order. Conversely, applications that prioritize real-time delivery, such as video conferencing tools, online games, and VoIP services, often opt for UDP. These applications can tolerate some loss of data but cannot afford delays. For them, the speed and reduced latency offered by UDP outweigh its drawbacks. To illustrate, imagine you're watching a live sports event online. Using UDP, the platform might skip a minor frame or two to keep the stream smooth and immediate, whereas using TCP could result in a frustrating delay, waiting for lost frames to be resent. Choosing the right protocol is crucial, as it directly affects the application's performance and user experience. Every application on your device communicates through a specific door known as a port number. Imagine a bustling city with countless buildings. Each building has a unique address that helps people find the right place. Similarly, in the world of computer networks, port numbers serve as unique addresses for different applications to ensure data packets reach their correct destination. Port numbers are essential components of both TCP and UDP protocols in the TCP/IP suite. They allow these protocols to effectively distinguish between multiple applications running on the same device. For instance, a web server typically uses port 80 for HTTP, while an email client uses port 25 for SMTP. These dedicated port numbers ensure that emails don't end up on a web server and vice versa. Moreover, port numbers enable multiple applications to share the network simultaneously. Each application uses a distinct port, allowing them to operate independently and efficiently without interfering with one another. This architecture not only maximizes the use of network resources, but also enhances the overall performance and security of data transmission. Port numbers help keep our digital traffic organized and flowing smoothly. As we've seen, TCP and UDP are fundamental to the functionality of the Internet and our broader networked world. To recap, Transmission Control Protocol, or TCP, is the muscle behind ensuring that every byte of data you send is received exactly as intended. It's like a meticulous librarian who makes sure every book is returned to the right shelf, in the right order. TCP achieves this through a series of handshakes, acknowledgments, and retransmissions, making it indispensable for applications where accuracy is paramount, such as web browsing, emails, and file transfers. On the flip side, we have User Datagram Protocol, or UDP. Think of UDP as the speedy delivery driver who prioritizes quick delivery over checking if all packages are accounted for. UDP sends data packets without waiting for an acknowledgement, or even establishing a connection, which can be a boon for real-time applications like video streaming, online gaming, or broadcasting live events. While it might drop a few packets on the way, the overall speed gain is often worth the trade-off. Both these protocols operate using port numbers, a system that allows a single device to manage numerous network connections at once. This is akin to having multiple doors in a building, each leading to a different service or room, enhancing the efficiency and organization of data transmission. The interplay between TCP and UDP provides a robust framework that supports the vast array of internet functionalities we rely on every day. From ensuring that your video call is smooth and uninterrupted to guaranteeing that your bank transaction is secure and error-free, these protocols are the unsung heroes of our digital age. So, whether you're a gamer, a streamer, or just sending an email, the seamless operation of these protocols is what allows you to do so without a hitch. It's a complex technology that works tirelessly in the background, ensuring that your digital interactions are as smooth and reliable as possible. Next time you stream a movie or send an important email, remember the sophisticated dance of TCP and UDP working in the background to make it all happen seamlessly.